Hey guys, welcome back to Pandas Data Diaries. Today I want to show you how to find the null space or the kernel of the matrix, and I will do this as always using SymPy in Python. So let's start right away. First of all, I will load SymPy and some config libraries so that I can display the calculations. So that's done over here, and I will load a sample matrix A. So just using sp, which stands for sympy.matrix, and give it these values over here in these arrays. And it will display as such. So you see the matrix over here. And the first thing that we have to do to find the null space will be to run some row reduction steps. We can simplify this by using this command over here, which is called lu decomposition. I will not worry so much about the details of this function for now, and not about L and not about P. I'm just interested in U, which is the upper triangular matrix. So let's run this step and let's see what we're getting back. So when we do this, basically what it does is it runs some row reduction steps. And if you don't know what it is, please check out my previous videos where I explain these steps. But it will reduce the matrix to this upper triangular form. So we have this triangular over here, and the rest is just zeros. We can further simplify this matrix, but I will not do it for now because I want to show you the next steps, how you would manually find the null space. So we will keep it as such. And we will now have to identify the pivot and the free variables. So I already prepared it over here. Let me show you. So this is here highlighted. The blue ones are the pivot variables. So the leading numbers in the rows, usually it's a 1. Here's a 2, but you can divide the entire row by 2, then it will also be 1. So the leading entries are the pivot variables. This row doesn't have any pivot variables, it's just all 0, so it doesn't add anything. That is because this row is not linearly independent, so we're only interested in these two actually. And the columns containing the pivot variables are also the pivot columns, so the green ones. Okay, now that we've identified the pivot variables, what we can do is back substitution. So I already prepared this as well. So what can we do? Basically, this system, the matrix, can also be rewritten in the equation form. So that would be just the same information. You have 1 over here, x1 plus 2, 2, 2, 2, plus 2, 2 over here. So, and the same for the second row. It is just 2x3 plus 4x4. So these two over here. Okay. And now what we can do is we can solve the system for the pivot variables in terms of the free variables. So remember, these are the pivot variables over here, x1 and x3, and we want to express them in the form of the free variables. So let's do this. First of all, starting with the second equation, because we want to do back substitution, so it's easy to start from here. And what we see is we have this equation over here, 2x3 plus 4x4 equals 0. And when we solve this for x3, we just get minus 2x4. So just bringing this over to the other side and doing the basic algebra. Okay, we can do the same when we substitute x3 back into the first equation. So we now have x3 minus 2x4, and we want to substitute this in the first equation over here. So doing this, we get for the first equation x1 plus 2x2 plus 2, and here we have to substitute minus 2x4 plus 2x4 equals 0. And when we then do the basic calculations and solve for x1, we will see that it is minus 2x2 plus 2x4. Okay, now we have the two variables. So x3 can be expressed as minus 2x4, and x1 can be expressed as minus 2x2 plus 2x4. Okay, and now it's the fun part. So now what we can do is we can express this whole vector in the following format. We can just put in the results that we have solved for. So we have the x1, which we know is can be expressed as minus 2x2 plus 2x4. We just put it in over here. So we have minus 2x2 plus 2x4. And we also know that x3 can be expressed as minus 2x4. So these are these minus 2x4. Okay, and the rest just stays the same. And then when we want to get the so-called special solutions, I will get into the difference of special and general solution later. But the special solutions, what we can do is we can apply a certain algorithm. We can just set each free variable to 1 and that at a time. And we set all the other free variables to 0. We could also choose other numbers, but 1 and 0 is just convenient. So we just choose 1 and 0 as a general algorithm. So when we do this, first we set x2 to 1 and x4 to 0. And we did it over here. So you see we have the same one over here, minus 2 plus 2x4. We just set the x2 to 1 and the x4 to 0. And over here, it's also x4, we also set it to 0. You see, these are these values represented. And then when we solve it, we get minus 2 times 1 plus 2 times 0, it's just minus 2. This stays the same, this turns to 0, and this also 0. Okay, we do the same now. In reverse, we just set x2 to 0 and x4 to 1. So putting it into the equation, this one means minus 2 times 0 plus 2 times 1 is 2, 0, and here minus 2 as well. And the rest stays the same. So this is just an easy way to find the special solutions. And these are the results. But there's one thing that is important to note is it doesn't end here, because we have a look at the general solutions as a linear combination of special solutions, because these here, as we just chose some arbitrary values for 0 and 1, it could be any multiple of it as well. So we can express this by just adding this scalar over here by saying C1 or C2 or C or D or whatever. It can be multiplied by any value, and still the linear combination of these two will be in the null space of the matrix or the kernel of the matrix. So here's the entire process that you go through to find the vectors that lay in the null space of the matrix. Of course, there's an easier way to do it with SymPy right away. So there's a function that does it, but I wanted to show you the process just for education. But here, if you want to use the standard function, same thing, you load the matrix and display it over here, and then you can just simply use this command, which is just dot nullspace, and it will return the result. And since it is basically it's an array or list, you can iterate over this list and then display all of the vectors that are in the null space. So let's do this separately, and we run it, and you will see we have the matrix A printed out and the null space of the matrix A. So the basis vectors are the same ones that we just found above. And of course, if you want to express it as a general solution, you would have to add the scalars before them. So C times this and D times that, or something like that, and get the linear combination. Okay, awesome. I think that's all that I want to show you for today. Thanks for watching. Don't forget to like and subscribe, and see you again soon on my channel.